All right, if you've ever really dug into a physics curriculum, you know this book, i.e. Irodov's Problems in General Physics. It's kind of legendary for being tough, right? Well, today, we're going to tackle one of its classic problems, the triple disk collision. It might look a little scary at first, but trust me, we're going to walk through it together, and you'll see it's totally manageable. Let's jump in. So before we get lost in any equations, let's think about something you've probably seen a million times. A perfect break in a game of pool. The cue ball hits the rack, and the balls scatter. But not randomly. It's predictable. Why? Well, it's not magic. It's all about geometry. The exact points where the balls touch and the angles they make, that's what decides where everything goes. Our problem today is basically a simplified, perfect version of that, and it's an amazing way to see how the starting layout dictates the entire result. So here it is, the problem itself, number 1.176 from Irodov. The setup is simple enough, right? We've got disk A moving with some speed v, and it's going to smack into two other disks, B and C, at the exact same time. And the key is it's a perfectly elastic collision. Now the real question, the heart of the problem, is what happens to disk A after the crash? Does it bounce backward? Does it stop dead in its tracks? Or does it just keep moving forward? It turns out the entire answer depends on just one little thing: how far apart disks B and C were to begin with. Okay, let's break down the wording here, because every word in a physics problem matters. Identical disks just means they all have the same mass, which we'll call m. Smooth plane? That's a gift. It means we can totally ignore friction. Now, elastic collision. This is the most important clue in the whole problem. It tells us that not only is momentum conserved, but kinetic energy is too. Simultaneously means the impact is perfectly symmetrical, which will make our lives way easier. And our goal? Find the final speed of disk A, which, as the problem hints, will all come down to a single number, eta, which is all about that initial spacing.
So before we even think about writing an equation, we got to get our toolkit ready. For any collision problem like this, there are basically two big, powerful laws that do all the heavy lifting for us. Let's lay them out.
Tool number 1, conservation of momentum. You've heard of it, right? Basically, the total oomph of the system before the collision has to equal the total oomph after. But here's the tricky part. And this is a really common pitfall. Momentum is a vector. It has a direction. That means we can't just add up the numbers. We have to look at the motion along the x-axis and the y-axis separately.
And our second tool? It comes from that one little word in the problem, elastic. This word is like a secret key. It unlocks the law of conservation of kinetic energy. It means no energy is lost to heat or sound in the collision. And the best part? Energy is a scalar. It's just a number, no direction to worry about, which makes the math so much nicer. With just these two laws, we have everything we need.
Okay, tools are on the table. We know the physics. Now comes the part where we turn these ideas into actual formulas. Let's map out our plan of attack.
And here's how we're going to do it. Just 3 steps. No need to get overwhelmed. First, we'll set up a smart coordinate system to make things clear. Second, we'll use a little bit of geometry to figure out the exact angle of the hit. And finally, we'll take our 2 big laws and write them down as equations. If we stick to this plan, this scary-looking problem becomes totally doable.
So, step 1, setting up our map, our coordinate system. Let's make our lives easy. We'll put the x-axis right along the path that disk A is traveling. Now, because of that simultaneous hit, everything is perfectly symmetrical. It's like a mirror image across the x-axis. So if disk B gets knocked off at some angle alpha, we know disk C is going to get knocked off at negative alpha. So the big thing we need to figure out right now is that angle, alpha.
So how do we find that angle? Check this out. It's all just simple geometry. At the exact moment they touch, you can see that we can draw a right-angled triangle connecting the centers of the disks. The hypotenuse is just 1 diameter, or 2 times the radius. The side opposite the angle is half the distance between B and C. The problem tells us that distance is related to eta, so we just use some good old high school trig, SOHCAHTOA. TOA. Sine of alpha is the opposite side over the hypotenuse. The radii cancel out, which is super convenient, and we're left with this really clean relationship. Sine of alpha equals eta over 2.
Okay, geometry's done. Time to write our first big equation, momentum in the x direction. Before the crash, it's easy. It's just disk A moving, so the momentum is mv. After the crash, disk A has a new velocity. Let's call it v prime. And what about B and C? Well, they fly off at that angle alpha, but we only care about the part of their motion that's along the x-axis, which is their final speed times the cosine of alpha. Since there's 2 of them, we add that in twice. And look, the mass m is in every single term, so we can just cancel it out and simplify our lives. There's our first equation.
All right, equation number 2, kinetic energy. This one's even nicer. Before the collision, all the energy is in disk A, so it's 1/2 mv squared. After, well, all 3 disks are moving, so we just add up their individual kinetic energies. And again, just like before, we see a common factor. This time it's 1/2 m in every term. So we can just cancel it out. And boom, there's our second equation. See how much cleaner this one is? No cosines, no angles. That's the beauty of scalar energy.
And just like that, the physics part is over. Seriously, we've done it. We've taken a physical event and turned it into 2 solid math equations. Now all that's left is to roll up our sleeves and do some algebra.
Okay, so here's what we're working with. Our momentum equation and our energy equation. We've got 2 equations, and we have 2 things we don't know. V prime, which is the final speed of disk A and the answer we want, and V final, the speed of the other 2 disks. That V final is just kind of getting in the way, so the plan is simple. Use these 2 equations together to eliminate it.
The classic way to do this is with a method called substitution. We're going to take one equation, rearrange it to get that annoying V final all by itself on one side. Then we're going to plug that whole expression into the second equation. It might look a little messy for a second, but it's totally manageable. We're just carefully grinding through the algebra to get one single equation with just the one thing we actually want to find, V prime.
So you grind through all that algebra, you simplify everything down, and voila! This is what pops out. Look at that. The final velocity of our disk, v prime, is just its original velocity, v, times this fraction. And what's in the fraction? Only eta, that geometric parameter we started with. This is so cool. It means the final speed, the direction, everything about disk A's fate comes down to where those other disks were placed at the very beginning.
Okay, we have our formula. Awesome. But in physics, just getting an equation isn't the end of the story. The real question is, what does this result actually mean? What does it tell us about what's physically happening? This next part is where the real physics insight comes in.
So let's circle back to the very beginning. Remember the core question? After the collision, what happens to disk A? Does it bounce backward, stop, or keep going? Well, this formula we just found holds the key. All we have to do is look at the sign of V prime. Is it positive, negative, or just plain 0? That will tell us everything. But wait, before we start plugging in numbers, we have to think about what makes physical sense. That number, eta, can't just be anything. Think about it. If eta is too small, say less than 1, the disks would be overlapping, which is impossible. And if it's too big, greater than 2, disk A would hit one disk and then the other one later, not at the same time. So eta has to be in this specific range. That's the only place where our problem even makes sense.
And here it is, the grand finale. It all boils down to one magic number, the square root of 2, about 1.414. If your spacing, eta, is less than that, look at our formula. The top part becomes negative. V prime is negative. That means disk A literally recoils and bounces backwards. Now, what if eta is exactly the square root of 2? The top of the fraction becomes 0. The whole thing is 0. The disk stops, dead in its tracks. And finally, if eta is bigger than the square root of 2, the top is positive, and disk A keeps moving forward just a bit slower than before.
So what's the big takeaway from all this? It's something really profound. The entire outcome of this complex 3-body collision, this whole dance of recoiling, stopping, or moving on, it's not random at all. It was completely decided before the collision even happened by one single number that described the starting geometry. That's the predictive power of physics.
And that leaves us with a really fascinating final thought to chew on. We just saw how a tiny little change in that initial spacing completely changed the future of disk A. This idea has a name. It's called sensitivity to initial conditions. And it's the heart of something you might have heard of called chaos theory. It's why predicting the weather is so hard, and it shows up everywhere. A tiny, almost unnoticeable nudge at the beginning can lead to a massively different result down the line. Pretty wild, right? Thanks for diving into this with me today.